Hello everyone, welcome back to Chapter 9 Lessons. Mrs. Hanson here once again, ready to discuss acid-base strength. What does it mean to be a strong acid versus a weak acid? What does it mean to be a strong base versus a weak base? And the answer to that lies with the degree in which an acid or base dissociates when placed into water. The splitting apart of a covalent molecule, or really an ionic compound, is called dissociation. When a strong acid is dissolved into water, it will 100% dissociate into its aqueous ions. We had given an example earlier of hydrochloric acid, HCl. In its gaseous form, it's not an acid at all. It would be called hydrogen chloride. Acids and bases only exist in aqueous solutions. And we wrote out this reaction for Bronsted-Lowry. We said 100% of this reaction pushes forward and a proton is transferred. Now remember, a proton is transferred from the acid to the base. And so therefore, HCl being an acid donates its proton. The water acting as a base accepts the proton. We see that a conjugate acid of hydronium forms for water, and the conjugate base of chloride is formed from the HCl. 100% of this reaction pushes in the forward direction. This is the very definition of the term strong. 100% goes from the left to the right. We see that a single reaction arrow is used because it's not in equilibrium. There is only one direction only, and that's the forward direction. The product is greatly favored. There are strong acids that we should memorize because if we memorize the strong acids, we'll then also know all of the weak ones as well. HCl, hydrochloric acid, is a strong acid. When it's placed into water, it will 100% dissociate into its aqueous ions. HBr, notice those are the halogens excluding fluorine. Hydrochloric, hydrobromic, hydroiodic are strong acids. They 100% dissociate. Sulfuric acid, sulfuric is known as battery acid. It also 100% dissociates into its aqueous ions, as does nitric acid. If I can remember these strong acids, I'll also know that any other acid is considered weak, and it only partially ionizes. Hydrochloric, hydrobromic, hydroiodic. Sulfuric and nitric acid are all strong. 100% dissociates. When a weak acid is placed into water, only a small fraction of the acid dissociates into its aqueous ions. And therefore, since it sets up an equilibrium, we'll see that we have a forward and a reverse reaction occurring. We have a dynamic equilibrium where the reactants are actually favored. Let's take a look at an example of acetic acid. Hydrogen acetate, acetic acid. It's the major ingredient in vinegar. Now you may see acetic acid written as HC2, H3O2. Hydrogen acetate. You see this acetate. 8 turned to ic, and we called it acetic acid. I also asked you to know that when you see this COOH, that you recognize that as the carboxylic acid functional group of organic chemistry. And that's our second semester, I realize, but we're just letting you know ahead of time that when you see the functional group written with a hydrocarbon chain, COOH, it's a carboxylic acid, and this right here is the proton that will be transferred during the acid-base reaction. So notice the acetic acid formed its conjugate base, and it's this last proton that was removed. This is called the acetate polyatomic ion. Water, of course, accepted the proton and formed its conjugate acid. Water acted as a base in this acid-base proton transfer. So with this example, when we say an acid is weak, it's because we only have a partial amount, like only 1% of the reaction proceeds in the forward direction, but the vast majority of the ingredients in the water here are lying to the left in the equilibrium. So the left side of equilibrium is being favored. Here are some examples of weak acids. Phosphoric acid, H3PO4, from that polyatomic ion called phosphate. 8 turns to ic, and we get phosphoric acid. Hydrofluoric acid, carbonic acid, and hydrocyanic acid. I'm practicing our naming skills. Do you hear that? Phosphate turns to phosphoric. Hydrogen fluoride, so we say hydrofluoric. This is carbonate, so it becomes carbonic acid. This is cyanide, IDE, so hydrocyanic acid. Keep practicing your naming skills. What's the difference between a strong acid and a weak acid? A strong acid will 100% dissociate, so we have just one arrow pointing in the forward direction. A weak acid does not set up a 100% dissociation. It sets up a dynamic equilibrium, so you'll see two arrows, one in the forward direction, one in the reverse direction, where the left side of the equilibrium is highly favored. Weak acids do not ionize as well as strong acids. So when we see a strong base in water, same story, it will 100% dissociate into its aqueous ions. We know that sodium hydroxide comes out as from the bottle as a solid white flake, if you will. And when it's put into water, it dissociates into its aqueous ions of sodium and hydroxide. These aqueous ions separate from the salt there 100%. So notice the term strong. Look at the arrow. It only points in the forward direction. Some common strong bases occur any first family metal. You could have sodium hydroxide, potassium hydroxide. Think about that first family metals, lithium hydroxide, cesium hydroxide. All of these are from the first family known as the alkali metals, group 1A. All of those represent strong bases. So how about a weak base? For example, ammonia is a weak base. Now it's a base because we've learned it has a set of electrons on the nitrogen and therefore can accept a proton. And when it does so, it accepts the proton from water, forming its conjugate acid, ammonium. Remember, it's a proton acceptor. So those sets of dots on the nitrogen now accepted a hydrogen ion. And water would need to act as the acid, donating the proton, forming its conjugate base, hydroxide. But I want you to focus on the arrows. The arrows say a dynamic equilibrium was set up where we have a forward reaction and a reverse reaction occurring. But the reverse reaction is much more successful. About 99% of the ingredients in this equilibrium lie to the left. The left side is favored. Here is a list of strong acids. Here is a list of their conjugate bases. Notice what's happening as we look at the bottom heading up. We're increasing in strength of the acid. Strong acids dissociate and release their ions. Weak acids do not dissociate very well. Dissociate means to separate into their aqueous ions. What is the trend that you see on this chart? Notice that the very, very strong acids, such as hydroiodic, hydrobromic, hydrochloric, sulfuric, and nitric acid, these are the ones that I recommended you memorize as strong acids. They have the weakest conjugate bases. A strong acid has a very weak conjugate base. And the flip would be true as well. Do you see that? That the strongest bases are down here. So a weak acid down here, a weak acid would have a very strong conjugate base. Let's try reading this chart. Is phosphoric acid or hydrofluoric acid stronger? Well, let's find them on our pKa chart here. Let's find them on this chart. H3PO4, phosphoric acid. How about HF? Do you see that? HF lies right underneath it. Which one is the stronger acid? Well, the acid strength increases as you go up. Phosphoric acid is higher on this chart. So phosphoric acid is stronger than hydrofluoric acid. Now, I want you to know this chart is given on your test-taking tool page. You do not have to memorize it. It's given to you. Perhaps you've noticed it, perhaps you've not yet looked, but it's been there the whole semester. It's probably the last image that appears because it's the last image we've needed. We're already all the way to chapter 9. So when I want to know which acid is stronger, I just find them on this chart. Higher up on the left side are the stronger acids. Now, let's see. Draw the conjugate base of each acid and predict which base is stronger. Now, this tells me when I find the conjugate base, oops, I should make that yellow. Dihydrogen phosphate is the conjugate base of phosphoric acid. Fluoride ion is the conjugate base of hydrofluoric acid. Remember that the bases increase in strength as you go down. So the fluoride is a stronger base than the conjugate called H2PO4 negative. That's called dihydrogen phosphate ion. Strongest acids, top left. Strongest bases, bottom right. And therefore, what that means, a stronger acid produces the weaker base. The weaker acid produces the stronger base. And this is what the direction of our chart shows us this. That's a really funny U, isn't it? Shows us this. There we go. So what is the stronger acid in each pair? Which acid has the stronger conjugate base? Pause your video and use your test-taking tool page and see if you can come back when ready and check your work. Pause, give yourself think time, and come back. All right, welcome back. I went and grabbed our chart just to have ease of convenience for seeing it here. We're going to compare sulfuric acid with phosphoric acid. So when asked which is the stronger acid, here's the strategy. I want to go and find each individual acid, sulfuric, H2SO4, and I'm going to compare it to phosphoric, H3PO4. Now looking at my chart, I can clearly see higher up on the list is sulfuric acid. So letter A, you wrote down sulfuric acid is the stronger acid. But which one had the stronger base? And of course, that would be the one further down on the list on the right side. So I'm going to make a list. Stronger acid, stronger base. The conjugate H2PO4 negative is the stronger base as compared to HSO4 negative. How about B? Now in letter B, we have HF, which is listed right here, and we're comparing it to HCl. Well, clearly we see the stronger acid is higher up on the left. HCl is the stronger acid, meaning that the conjugate base of HF is the stronger base. Pretty easy, right? Letter C, how'd you do? Well, let's check. H2CO3, that's called carbonic acid, compared to ammonium, which is NH4+. So those are right next to each other. The stronger acid is higher up on the left. H2CO3 is a stronger acid, meaning the conjugate base of ammonium, which is ammonia, is the stronger base. And one more in your set. You were asked to compare HCN, that's called hydrocyanic acid, to HF, which is hydrofluoric acid. HF, of course, is higher up, so it is a stronger acid, meaning that the cyanide conjugate base is the stronger base. When asked to predict strength, just use your chart. You are provided this chart in your test-taking tool page. Now, when we use acid strength to predict the direction of equilibrium, there's a general rule here we should know. When stronger acids and stronger bases are the reactants, on the left side, the reaction readily occurs and the reaction proceeds to the right. I want you to realize stronger always points towards the weaker side, always. That means if we had, and we don't here, but if we had a weak acid plus a weak base, and we have a dynamic equilibrium that would set up, strong acid, strong base. I'm just saying, if this had been the direction that we had written the reaction, I want you to know that the reaction would then favor this direction. Stronger will always point towards weaker. I'm going to write that in the margin. Recommend you do too. So if the stronger acid and the stronger base are on the left side, you'll notice this direction is being favored. If we have the strong acid and the strong base on the right side, this direction would be favored. We have to remember that stronger points towards the weaker side. So if an acid-base reaction where the stronger acid and the stronger base are on this side, we see that the opposite equilibrium is being favored. That means the reverse arrow favors the reactant side. Always, always strong points towards weak. So the equilibrium is going to favor the weaker side. Stronger acids, stronger bases dissociate and form the weaker conjugate pairs. Let's ask ourselves the following. And notice what I did here. I put a little clip art to make sure you see that this test-taking tool page is provided for you in the test. But it's a tool that we have to learn how to use as well. Alrighty. So are the reactants or the products being favored in the following reactions? This is my strategy. Step number 1, hook together conjugate pairs. Between the left and the right side, let's hook together the conjugates. Conjugate pairs only differ by the presence or absence of a hydrogen ion. Between HCN and CN negative, those are called conjugate pairs. The one with more hydrogen is always the acid. So HCN forming CN negative. Here's the other conjugate pairs, OH negative and water. Hydroxide would be labeled as the base, water would be labeled as the acid. We've just identified both acids. One will be on the left, one will be on the right. On the left side, HCN was the acid. On the right side, H2O was the acid. Step 3, find the stronger acid using your chart. And I'm going to say find the stronger acid using test taking tool page, the chart that I have put on the side here. Test taking tool chart. So let's find those. Where do we find HCN? It's right down here. And where do we find H2O? Well, it's right down here. Those are the two acids in this reaction. Who's the stronger acid? The one farther up is the stronger acid. So HCN is stronger, H2O is weaker. What does that mean for the dynamic equilibrium? We always point from stronger to weaker acid, right? So are the reactants or products being favored? The products are being favored because that is the weaker side. So your arrow, just to kind of give meaning to that, would point in the forward direction. In this dynamic equilibrium, the product side is being favored. Stronger always points towards weaker. So step 1, hook together the conjugate pairs. Step 2, identify the acids. One will always be on the left side, one will always be on the right side. Step 3, use your chart and find which one is stronger. Stronger will always point towards the weaker side. Let's try some more. I would encourage you to pause, give yourself think time, come back to me when ready. All right, well, let's try. Letter A. Letter A gives us HF going to F negative. Those two are conjugate pairs. HF is the acid. OH negative and H2O are the conjugate pairs. The conjugate acid of hydroxide is water. So the two acids that we're comparing in letter A is hydrofluoric to water. Hydrofluoric is found here on our chart. Water found way down here. Since hydrofluoric is the stronger acid, you said that the dynamic equilibrium would be favoring the right side, the product side. How about letter B? Start by finding your conjugate pairs and identifying the two acids. Between ammonium, NH4+, and ammonia, NH3, ammonium has more hydrogen, therefore, the left side, ammonium is acting as our acid. On the right side, HCl is the acid. Between Cl negative and HCl, this is the conjugate acid, the one with more hydrogen. We've identified the two acids. Now we're ready to compare. When we compare HCl, which is found way up here, compared to ammonium, which is found way down here, clearly we see HCl is stronger. And this simply tells me stronger points towards the weaker acid. So therefore, the reactants are favored in this dynamic equilibrium. How about letter C? Hook together the conjugate pairs. Bicarbonate, and carbonic acid are conjugate pairs. The one with more hydrogen is always the acid. Between hydronium and water, those are conjugate pairs. They only differ by the presence or absence of a hydrogen. And this guy, the hydronium, would be the acid. So on the left side, we have H3O plus, and on the right side, we have H2CO3. Those are the two acids in this acid-base proton transfer reaction. Now let's use our tool page to find the strengths. H3O plus, highlighted here. H2CO3, highlighted here. The higher up means the strength of the acid is greater. So H3O plus is a stronger acid than H2CO3. Therefore, strong always points towards weak, and therefore products would be favored. Did you get them? Oh, give yourself a big old star. It just feels good. We can play a role in dynamic equilibrium by expressing the products over reactants with an equilibrium constant. This is really the exact same lesson presented in the previous chapter on equilibrium. The equilibrium for an acid is expressed by taking the concentrations of the products over the concentrations of the reactants. Do you remember what that bracket meant? It's the concentration unit called molarity, which we've learned to be moles per liter of solution, big M. So for the reaction where an acid, let's just use a general formula, HA, to represent an acid. We know H is a +1 and an anion is a minus charge, so an HA. A general formula shows the dissociation of an acid forming its aqueous ions. And remember how we said to place products over reactants, where the little brackets here represent the concentration units in molarity. The K is what we call the equilibrium constant, the ratio of the concentrations of products over the concentration of reactants. Here are the products, the aqueous ion, hydronium, times the aqueous ion of the negative conjugate base, all over the initial concentrations of those reactants. Products over reactants. Remember, these are multiply, right? So when I say species A times species B and we have C, D, remember this is all multiply in those species. So when we multiply both sides by water, remember a moment ago, just to back up, if I were to multiply both sides by H2O, I can get rid of it on this side and bring it up to the left, and that's what we've done here. When we multiply both sides by the concentration of water, we can simplify this expression to let it become the acid dissociation constant. And that little A is going to represent the equilibrium constant for an acid. And therefore, it's the same expression, it just eliminates the water on the bottom of the equation. Which makes sense because water wouldn't have a molarity, it's the solvent. Whoops, I reversed that. I wanted to write expression. So if we take a look at just an example problem where we say, let's say we have H2CO3. And this would dissociate to release 2 aqueous ions of hydrogen. You know what? I'm going to reverse that. I'm going to put the water in, just to remind ourselves that we can eliminate it. So here's a proton transfer. Out comes an aqueous ion, the conjugate base HCO3 negative, and the conjugate acid of water H3O plus. So in this reaction, we have a proton transfer. Ka is the acid dissociation expression, where I'm going to take the concentration of the products, which would be the bicarbonate ion, HCO3 negative, times the concentration of the hydronium ion, H3O plus, set over the original molecular form of the acid, H2CO3. Do you notice how I do not include the water? So Ka, the acid dissociation expression. The larger the Ka value, so if Ka is large, and by large I mean a large in magnitude of size, you have a very strong acid. And the smaller Ka is, the weaker the acid. So remember, K values, they don't have a unit. They're just a number, but it's the magnitude of the number that's interesting to us. The larger numbers, the larger they are from 1, the stronger the acid is, the more it's going to favor the forward direction. In other words, stronger acids give us more aqueous ions. That's a large Ka value. The weaker the acid, the more the left side of the equilibrium is favored, and therefore the smaller the Ka value. So the magnitude of the number lets us compare acid strengths. Large Ka, strong acids. Smaller Kas are weaker acids. And now you can see a structure of this Ka. These are Ka values. The strong acids have large Ka values. The weaker acids have small Ka values. So you can see these are weaker acids. So which in each pair is stronger? Let's find HCN. HCN is hydrocyanic acid. You see it? And HSO4 negative. So when I compare these two, I have a Ka value of HCN is 4.9 times 10 to the negative 10th. For HSO4 negative, it's 1.2 times 10 to the negative 2. Which number is bigger? So think about what 4.9 times 10 to the negative 10. It's like 0.1, 2, 3, 4, 5, 6, 7, 8, 9, then the number 4, 9. That's a really tiny number. In this example, 0.012, that's what 1.2 times 10 to the negative 2 means. That's a bigger number. The bigger number represents the stronger acid. So in this example, who's stronger? Well, it's HSO4 negative. How about in the next example? Let's switch colors to blue. Acetic acid HCH3COOH versus ammonium, NH4+. So when I compare the Ka values, we have 1.8 times 10 to the negative 5th versus 5.6 times 10 to the negative 10. Clearly you see that acetic acid is a stronger acid as compared to ammonium. Bigger Kas, stronger the acid. Rank the acids in each group in order of increasing acid strength. And again, you would be provided a test-taking tool page to do so. Let's find our acids and compare their Ka values. In letter A, H3PO4, that's called phosphoric acid. compared to H2PO4 negative, compared to HPO4 2 negative, all families of phosphoric acid, taking off one proton, then the next, then the next. Who has the biggest number is the original H3PO4, the strongest acid. So this would be first. How about we do this? H3PO4 is stronger than H2PO4 minus, which is stronger than HPO4 2 minus. Let's try letter B. Let's find HCN. Here it is. Compare it to HF. Here it is. Compared to acetic acid, which is found here. Who's the strongest acid? Was the largest Ka? Would be HF, followed by acetic acid. Hear that COOH, your carboxylic acid functional group. That's your proton right there for acid-base proton transfer. And of course, the weakest then would be HCN with the smallest Ka value. Determine whether the reactants or products are favored in the following reaction. Do you remember our strategy? I want to know which side of the equilibrium is being favored. To do so, I want to hook together the conjugate pairs, those that only differ by a hydrogen ion, and I want to identify the acids on both sides of the arrow. So here I can see on the left side, bicarbonate is going to act as the acid, and on the right side, ammonium is acting as the acid. Just to remember how to label conjugate pairs, the acids in the pair always have more hydrogen. So now we have to find who is the stronger acid. We're comparing HCO3 negative right here in our chart. Compare that to NH4 plus, who's right here on the chart. Who's stronger? Well, I see this guy is stronger. And remember our rule? Stronger always points at the weaker acid. So are the reactants or products being favored? The reactant side. And that tool allowed us to find the stronger points at the weaker acid, always. Let's consider the weak acids HCN versus H2CO3. HCN, let's find them just to bring them out. HCN versus H2CO3. All right, so there's our eyes on the chart. Which acid has a larger Ka value? Well, I can see that right here. H2CO3 has a larger Ka value. It's assigned 4.3 times 10 to the negative 7, which is a bigger number than a magnitude of to the negative 10th power. That tells me the larger Ka is the stronger acid. Which acid has the stronger conjugate base? Well, do you remember our trend? Strong acids form weak conjugate base. You can flip that by saying weaker acids form stronger conjugate conjugate base. So when I told you that H2CO3 was the stronger acid, it's going to form the weaker conjugate base. And when I told you hydrocyanic was the weaker acid, it has the stronger conjugate base, Cn negative. So here, stronger acid, weaker conjugate base. The weaker acid made the stronger conjugate base. And when each acid is dissolved in water, for which acid does the equilibrium lie further to the right. Do you understand what it's saying? All it's saying is which one is the stronger acid. Further to the right is going to mean favors the product side. And that's the very definition of what a strong acid does. So remember that the definition of strong means that it's favoring the right side. So when I'm going to write pushes equilibrium to the right, you'll know what that means. It's being favored to the right side. So the stronger the acid, which was our H2CO3, it's the bigger Ka. It means it's lying on the right side of the equilibrium more so than an HCl. Let me model what that means kind of in a visual. H2CO3, when in water, forms a dynamic equilibrium that's going to favor the right side more so than what HCN would be able to do. So I'm just emphasizing that what strong versus weak means. The stronger acids favor the right side. The weaker the acid, the left side is being favored. So the stronger H2CO3 has more, the equilibrium is lying further to the right than for a weaker acid. Okay, good work on that problem. Take a moment to digest if you need to there. In our next step, we're going to talk about, I just wanted to see how long we've been talking. We're talking about dissociation of water and setting up the foundation of the pH scale. So, when water behaves as both a Bronsted-Lowry and a Bronsted-Lowry base and acid, we called it amphoteric. It can behave as an acid and a base. Two water molecules can actually collide together in an acid-base reaction. In one scenario, if water is acting as the acid, it forms a conjugate base, hydroxide. In the second scenario, if water acts as the base and accepts the proton, it forms its conjugate acid, hydronium. There is a proton transferred between two water molecules. Now, when we think about this, the OH negative, we recognize this as the base ion, and we recognize hydronium as the acid ion. When we take a look at products over reactants from that reaction, we come up with what's known as its equilibrium constant expression. A moment ago, we just had water plus water in dynamic equilibrium with hydronium and hydroxide. We're going to take the products, the hydronium and the hydroxide ion, and place them on the top of this expression. Since there's two water molecules on the reactant side, notice that this ends up to be squared. The equilibrium constant expression. So that means products over reactants, where the coefficients become the powers with which it's raised. Just as before, with Ka, we eliminate the water. It really makes no sense to talk about the concentration of water. You can't have a concentrated solution of water and a dilute solution of water. It makes more sense to just drop it from the equation. So eliminate the water, and we get what's called the ion product constant for water. That's Kw for water. And all that's left then is the concentration of hydronium times the concentration of hydroxide, the acid ion and the base ion, when multiplied together, give a constant. You know what that means in math? A constant? It means it's always the same number. And if we look at that number, we can actually solve for it. It's 1 times 10 to the negative 14. Here's how we know that. Experimentally, we can find that when two water molecules collide together, they release ions that are both valued at 1 × 10 to the -7th molar units. So when I multiply 1.0 times 10 to the -7 by itself again, we come up with this -14th power. This is a constant for all times of kW value. Do you see what we're lying down here is the foundation of the pH scale? Why is the pH of 7 considered neutral? Well, that's the concentration when both the acid and the base ions are the same. Why is the top of the pH scale 14? That's the top of the scale because it can't get any greater. When I multiply -7 by -7, the top of the scale is 14. We're setting up the pH scale as a numerical system of numbering from 1 to 14, where 7 is going to be considered neutral. That happens because the acid and the base ion are exactly the same concentration. That's the direction we're heading. Here's what we know. Kw is equal to the concentration of the acid ion times the concentration of the base ion, and we know Kw is a constant and that it always is 1 × 10 to the -14th power. Always. That's the term constant. So if we're given one concentration of an ion, we can easily find the other concentration by plugging it into the formula. For example, let's have a cup of coffee. The hydronium ion concentration, the acid ion concentration, is given to me as 1 × 10 to the -5th. Well, that tells me the Kw constant, 1 × 10 to the -14, is set equal to 1 × 10 to the -5th, which was the hydronium, times the hydroxide, which is what we need to solve for. What is OH going to be equal to? Just to isolate, we can see that it would end up saying 1 × 10 to the -14, which remember is what we called Kw, divided by the concentration of the hydronium ion, which was our H3O+. So we can isolate, solve for this by taking 1 × 10 to the -14, which I'm going to use my calculator and use my scientific notation. That's the EE key on my calculator. Remember, depending on your calculator, you might see EE, you might see EXP, or you might see 10 raised to the X power. Those are all scientific notation. It just depends on what kind of calculator you're using. Now let's hit that together on the calculator you have in front of you to be sure you're familiar with how to use it. 1 EE -14 divided by 1 EE -5. That EE means to me times 10 to the, however your calculator does that. And my answer, 1 × 10 to the -9, and that's molar units for hydronium. Oops, we solved for hydroxide. 14 minus 5 is 9. If we have an acidic solution, the acid ion concentration is greater than the base ion concentration, and thus your hydronium is going to be a larger number than 10 to the -7. In a basic solution, the base ion is in greater concentration than the acid ion, and thus hydroxide is going to be greater than 1 × 10 to the -7th units. Let's check this trend out in the following question. What if hydronium, remember what this is? It's the acid ion, in blood is 4 × 10 to the -8th molar units. what's the value of the base ion called hydroxide? And would it be acidic, basic, or neutral? Here's what we know. Kw is found by taking the concentration of hydronium times the concentration of hydroxide. And we know Kw is a constant. It's the top of the pH scale, 1 times 10 to the negative 14th units. Hydronium was given to us as 4 times 10 to the negative 8th molar units. We're being asked to solve for hydroxide. To solve for hydroxide, we're going to divide both sides by 4 times 10 to the negative 8th. And when I do so, remember your calculator sequence, I'm going to hit 1 EE negative 14 divided by 4 EE negative 8. And my screen reads 2.5 times 10 to the negative 7 molar units. Now, which number is greater? We have the H3O plus given to us as 4 times 10 to the negative 8th. We just solve for hydroxide as 2.5 times 10 to the negative 7th. When you multiply those two numbers together, you get 1 times 10 to the negative 14th. Which number is bigger? Remember what negative 8 would look like? 1, 2, 3, 4, 5, 6, 7, 8. Remember what this would look like? 1, 2, 3, 4, 5, 6. Which number is bigger? Well, this one is, isn't it? So hydroxide concentration is greater than hydronium concentration, meaning that the solution is slightly basic. There's more base ion in the solution than the acid ion. The larger number tells me that it will be basic. Let's calculate the following. Given the concentration of the base, let's find the concentration of the acid ion and then indicate if it's acidic, basic, or perhaps even neutral. Remember our formula, H3O plus times OH negative is always a constant. The constant is 1 times 10 to the negative 14th. That's called the ion product constant for water. And it's the top of your pH scale, 1 times 10 to the negative 14th power. Now in this reaction, H3O plus is what we're trying to solve for, given a variety of OH negatives. So for instance, letter A, 1 times 10 to the negative 6 is given as our hydroxide. So to solve for this, 1 times 10 to the negative 14th divided by 1 times 10 to the negative 6, that's taking Kw over hydroxide, and you're going to find hydronium. So let's hit that together. 1 EE negative 14 divided by 1 EE negative 6. And my screen reads 1 times 10 to the negative 8th molar units for hydronium. Which is the bigger number? If hydroxide is 1 times 10 to the negative 6th, and hydronium is 1 times 10 to the negative 8th, you can see hydroxide is greater in concentration than hydronium. Do you see that? This is like writing 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's the concentration of hydroxide. 1, 2, 3, 4, 5, 6, 7. There's your concentration of hydronium. This is the larger number, so the solution is going to be basic. Let's try letter B. Letter B, we're going to solve for hydronium, same process, 1 times 10 to the negative 14th, which is your Kw, divided by 1 times 10 to the negative 9th, which is your OH negative. And when you do so, you're going to solve for hydronium. 1e negative 14 divided by 1e negative 9. What'd you find? Well, it's 1 times 10 to the negative 5th power. Which one is bigger? Here you have hydronium to the negative 5th. Here you have hydroxide to the negative 9th. This time your hydronium ion is in a larger concentration than hydroxide ion. The solution will be acidic. Letter C, let me come down here. 1 times 10 to the negative 14th, that's our Kw, divided by 5.2 times 10 to the negative 11th, that's your hydroxide. That'll solve for hydronium. Let's find it. 1e negative 14 divided by 5.2 e negative 11. My screen says 1.9 times 10 to the negative 4th molar units for hydronium. These are all molar units. I shouldn't be laxing on that. There we go. Which one's bigger? Oh yeah, you're right. The hydronium, its concentration to the negative 4th power is a larger number than the hydroxide, who has a value of negative 11. So that means this solution is acidic. There was one more. Let's work it here. 1 times 10 to the negative 14th is our ion product constant for water. We'll divide that by 7.3 times 10 to the negative 4. That's our hydroxide concentration. And when we do so, we're solving for the acid ion called hydronium. Let's hit it together. Here I'm reading 1.36 times 10 to the negative 11th power for the concentration of hydronium. Well, this time the base ion was in a greater concentration than the acid ion, meaning the solution came out basic. Since strong acids and strong bases dissociate 100%, that's the definition of being strong, their molarity tells us directly the concentration of the acid and base ion, respectively. So a strong acid and a strong base, a 0.1 molar HCl tells me it has 0.1 molar of the acid ion. And if I had a 0.1 molar sodium hydroxide, I would know that the base concentration was also 0.1. So strong acids and strong bases, their concentration indicates the concentration of the acid and base ion directly. Let's see that in action. We have a 0.01 molar sodium hydroxide solution, 0.01 molar NaOH. Now here's what we know. When NaOH dissociates, 100% of it forms aqueous ions of Na plus and OH minus. That this 0.01 molar NaOH gives us the concentration of the hydroxide. It's also the concentration of the sodium ion. We get equal amounts of ions that dissociate. But this is what's used to calculate the other. I know that Kw is equal to the concentration of the acid ion times the concentration of the base ion. I know that Kw is a constant, that it's the top of the pH scale, 1 times 10 to the negative 14th. And when I place in the value of 0.01 molar for the concentration of OH negative, I can find H3O plus. Let's do that. 1 E negative 14 divided by 0.01, and your screen should read 1 times 10 to the negative 12th molar units for that concentration of hydronium. So what does that mean? Well, that solution is very, very basic, isn't it? Because the OH negative is clearly larger, those are greater than signs, greater than the H plus. And therefore the solution is very basic, which you would expect with a strong base such as sodium hydroxide. Let's calculate the value of H3O plus and OH negative in each of these solutions. I want you to recognize, are you being given the acid or the base? For example, in letter A, NaOH, that's going to be a base. So the concentration of the hydroxide ion is given as 0.001 molar. In letter B, we're given the HCl. Well, you recognize that as an acid, right? And so the acid ion is going to be given to us as 0.001 molar. And in letter C, HCl is an acid. So therefore, the acid ion dissociates and gives me the concentration of 1.5 molar. Same in letter D. NaOH is a base. And so this concentration is giving me the base ion of 0.3 molar. So I have to recognize if it's an acid or a base, and therefore I can pull out the concentration of the next ion. So in letter A, we already know hydroxide. We can solve for hydronium. Letter B, we'll need to solve for the base ion. In letter C, we'll need the base ion. And in letter D, we'll need the acid ion. Each time you're going to begin by saying 1 times 10 to the negative 14th. That's your kW. And you're going to divide it by the given quantity. So in letter A, when I put 0.001 molar down here, I know that's the base ion, and I'll find hydronium. In letter B, you'll have the exact same calculation. It's the same number, but it's going to represent the base ion. So here, since this was kW and this was the acid ion, you're solving for the base ion. All right, does that make sense? It's the same number, you're just representing two different qualities. Let's hit that. 1 E negative 14 divided by 0.001. This comes out to 1 times 10 to the negative 11th power. It's the same answer, it's just the opposite ion. In letter C, 1 times 10 to the negative 14th divided by 1.5. And that reads for me 6.67 times 10 to the negative 15th. Wow, that's really acidic because the base ion is incredibly small. One more. 1 E negative 14 divided by 0.3. And that's 3.3 times 10 to the negative 14th molar units. All right, we're doing great. Using kW to solve for the ion product constant for water. Now, let's take a break here. I'm going to stop the video. We've been going about an hour. When you take a break, come back for the next lesson. I'd like to introduce the pH scale, and you're going to find this is just so wonderful because we don't have to worry about these tiny, tiny numbers anymore. Take a break, come back for lesson 3 when ready.